All right, welcome to week 2's practice video. I figured I'd kind of just spend this video with a little bit of a limit marathon. I have a whole bunch of limits lined up, and I'm going to kind of just spend some time on each of them, how I would think it through, how I would work on it, things like this. So let's start right here. I think I have 10 total. Okay, so first thing I'm going to observe is that if I plug 0, first of all, I'm going to observe that this doesn't even make any sense. Switch that to an X. If I plug 0 in for X, what is going to happen is I will get a 0 right here. That I'll have a square root of 16, that's 4. 4 minus 4 is 0. And in the denominator, I would also have a 0. So in my brain, I'm thinking to myself, oh, that's indeterminate form. 0 divided by 0. And indeterminate means that nothing can be concluded yet. Sometimes it means the limit doesn't exist. Sometimes it means it does exist. You just have to do a little bit of algebra to discover it. And I think that's what's going on here. So I'm going to go ahead and start with some algebra. And the famous trick that I always go to is multiply by 1. So that's what I'm going to do. This is the same thing as the limit as x approaches 0 of the square root of x plus 16 minus 4 divided by x times 1. Okay, so I'm multiplying 1 by the thing inside of the limit. I see the square root and I don't like it, so I know a mathematical trick. This guy right here kind of looks like an a minus b. And I know an a minus b has a best friend such that when you multiply a minus b by this best friend, I get this a squared minus b squared. It's called the difference of squares. And notice that a here, which has a square root, would get unsquare rooted here if I can choose the right thing. Of course, hopefully we know what this is. All right, I'm going to skip just a little bit of a few steps. If you don't like my move, these guys would cancel, and that gives you right back to where we started. So I haven't made any sort of mathematical errors. Also, this is always positive, this is always positive, so I didn't accidentally multiply by 0 over 0. That is 1. So now what do? I simply FOIL, or I just recognize the difference of squares. That's what I'm going to do, and say that's the same thing as x plus 16 all squared minus 4 squared. It's going to be all divided by x times the square root of x plus 16 plus 4. And this is me doing some algebra to hope for the best. I hope once I clean this up that I won't have a 0 over 0 situation. So let's see what happens. This is the limit as x approaches 0 of x plus 16 minus 16. Oh, that's nice. Divided by x times the square root of x plus 16 plus 4. These guys cancel. Oh, and then the x's cancel. So all I have left is the limit as x approaches 0 of 1 divided by the square root of x plus 16 plus 4. And I recheck. What happens if I plug 0 in right here? Am I still dividing by 0? And the answer is no. All I would have is 1 over, and notice this is the first time that the limit does not show up. Including this limit the whole way through is really, really important. People who are new to limits will drop the limit and they'll just change this part, and you'll run into big problems if you do that. Make sure the limit is there until this moment right now when I'm actually going to take the limit. All I've done so far is algebraic manipulation within the limit. This is the same thing as 1 divided by the square root of 0 plus 16 plus 4. And that's the same thing as 1/8. Okay. Limit 2. That was fun. All right, let's see what's going on right now. Let me try plugging -5 in. -5 in right here. That's going to be 1 over -5 squared. That's 1 over 25. Oh, shoot. 1 over 25 minus 1 over 25. That's a problem in the numerator, or it's not a problem if it's just in the numerator. But if we notice down here in the denominator, if I plug -5 in right here, indeed, it's going to be -5 plus 5. So I have work to do. Naturally, my natural response to this limit is I kind of want to add fractions, or in other words, find a common denominator. And again, notice that I'm writing the limit every time. That is really important. So finding a common denominator shouldn't be new to us. All divided by y plus 5. Okay, I got that common denominator in the numerator. So what I have in my numerator now is, I have the limit as y approaches -5, y squared minus 25, all divided by 25 y squared, all divided by y plus 5. A little bit more algebra, that takes me here. That is the limit as y approaches -5 of y squared minus 25 divided by 25y squared times y plus 5. And again, because this is simply multiplying by the reciprocal, so in the denominator I have y plus 5 over 1, multiply by the reciprocal, and multiply across. All right, hopefully we're noticing something. That difference of squares seems to not leave this topic, and indeed, we are going to use the limit, the difference of squares many times here. So we have the limit as y approaches -5 of y minus 5, y plus 5, all divided by 25, y squared, times y plus 5. And we are victorious because check this out. These guys cancel. And then after I do that, I'm going to recheck and see if I still have a problem in my fraction, and it doesn't look like I do. I have -5 squared times 25. That's not 0, so I can take the limit. What it looks like I get is -5 minus 5 in the numerator, and then 5 to the 4th power in the denominator. That is the same thing as -2 over 5 to the 3rd power, canceling a 5. That's the same thing as -2 over 125. Ooh, a mosquito. Stand by, guys. Ah, dang it. Missed it. All right. Next. This is going to be a marathon. Thank you for chugging away with me. All right. So we got the limit as b approaches 7. Oh, man. What the heck is going on here? This looks similar to something I feel like we've already done. It does look a little bit more complicated, though. Well, I know what my first move is going to be. It's going to be multiply by... Well, first of all, let's check if this is even a problem. Letting 7 go right here. Okay, so that's 49. I need help. One, 5, that's 12. 625. Okay, yeah, the square root of 625 is famously 25. So we do have a problem. Oh, you see, I'm only checked the numerator. The numerator is 0, but clearly the denominator is 0 too. So we do have a little bit of work to do. So let's go with the limit as b approaches 7 of the square root of b squared plus 576 minus 25, all divided by 7 minus b, but now I'm going to multiply by 1. Okay, what version of 1? This version of 1. We call it the conjugate of this guy right here, the square root of b squared plus 576 plus 25, all divided by the square root of b squared plus 576 plus 25. Never 0. Both of these terms are positive. And let's see where this takes us. We recognize the difference of squares. This is the limit as b approaches 7 of the square root of b squared plus 576 all squared plus, or excuse me, minus 25 squared all divided by, looks like 7 minus b times, put that in parentheses, the square root of b squared plus 576 plus 25. All right, let's see where this takes us. It looks like I got the limit as b approaches 7. And the numerator, I just have a b squared plus 576 minus 25 squared. Okay. I know 25 squared is 625, so let me actually replace that. And this is all divided by 7 minus b times the square root of b squared plus 576 plus 25. Okay, shoot. It's too hard for me. So that's going to be 9, 4, and 5's canceled. 49. Oh, okay, I'm seeing something. Yet another difference of squares. Man, this is crazy. All right. So what we have is the limit as b approaches 7 of b minus 7 times b plus 7, difference of squares in the numerator there, all divided by 7 minus b. Well, actually, I'm going to do a step here. Notice that 7 minus b can be rewritten as b minus 7, but with a negative out front. Don't believe me? Just redistribute that negative. I would get a negative b. Redistribute the negative right here. I'd get a positive 7, so I think I'm good. And then I'd have the square root of b squared plus 576 plus 25, all in my denominator. These guys cancel. That was the entire point. I can take a negative out. This is the negative of the limit, this negative out. This is the negative of the limit as b approaches 7 of b plus 7 divided by the square root of b squared plus 576 plus 25. All right, let's see. Let's see if I can evaluate this. This is the same thing as negative 14 divided by the square root of 49 plus 576 plus 25. Notice that I don't have the limit anymore because I just took the limit because I noticed there wasn't a problem anymore. This thing in the denominator is always positive. All right, so that's going to be the same thing as 576 plus 50 is 626 minus 1. I've also done this a million times in the past, 5 minutes, so I don't know why I'm still challenged to see what that is. This is the square root of 625. That's 25 plus 25. That is negative 7 over 25. Let's go. All right, what a marathon. We're doing well. 13 minutes in, crushing 3 limits. I think we're good. All right, let's see what's next. Yeah, okay, things are ramping up. Let me stare at this. I'm going to have to do some serious math. Tag along with me if you so choose. I'm going to see what happens if I plug 2 in, because we might just be all good. Plugging 2 in the numerator, I get 8, and then 12, and then minus 68 plus 48. Okay, so 8 plus 12 is, oh shoot, we do have 0 in the numerator, but that in itself is not a problem. 8 plus 8, I'm checking the denominator right now, minus 26 plus 10. Yeah, we do have a problem. But implicitly, what that means is that t minus 2 is a factor of both the numerator and the denominator, all right? So what that means is I can use my handy-dandy synthetic division. Hopefully we've all recognized this. And since t minus 2 is a factor, then I know that 2 is a root of the numerator, all right? And then I list coefficients. What's the coefficient of t cubed right here? Let's say, first of all, I'm going to divide it into the numerator. What's the coefficient of t squared? That's 3. What's the coefficient of t? That's negative 34. And the coefficient of t to the 0 is 48. So here's what we got. I switched to yellow randomly. That's all good. 1, 3, negative 34, 48. Okay. And synthetic division, bring the 1 down, multiply, add, multiply, add, multiply. And we were expecting this to have a remainder 0. But the whole point of this is now I can say that therefore t cubed plus 3t squared minus 34t plus 48 is equal to t minus 2 times the coefficient of 1 less degree. So it's going to be a coefficient of degree 2, excuse me, a polynomial of degree 2. And the coefficients are sitting right here. So that's going to be 1t squared plus 5t minus 24. All right, so that's my numerator. Then I have to follow the same process with the denominator. So I've got 2, 1, 2, negative 13, 10. And again, these are coming from these numbers right here. Okay? Following synthetic division, hopefully that is review. Negative, what is that? Negative 5. Negative 10. There we go. And therefore, t cubed plus 2t squared minus 13t plus 10 is equal to t minus 2 times t squared plus 4t minus 5. All right, let's go. And therefore, taking this guy down here, that says that the limit as t approaches 2, I'm going to change the numerator to what I have it to be right here, t minus 2, t squared plus 5t minus 24, all divided by t minus 2. And of course, we are seeing why we're happy. T squared plus 4t minus 5. These guys cancel. And what I get is that the limit as t approaches 2, use your verbs, of t squared plus 5t minus 24, all divided by t squared plus 4t minus 5. And now, hopefully, I can plug in the limit. This is going to be 4. This is going to be 8. Yeah, we're far away from 5. So this is the same thing as 4 plus 10 minus 24, all divided by 4 plus 8 minus 5, simply plugging 2 in for t. And by the way, the reason I can do this, notice we are crushing limits a lot faster than with the epsilon delta proofs. And this is all with the help of the limit laws. Like in the background, I have the limit laws. For instance, right now, I just used that the limit of a quotient is the quotient of limits. And then in my numerator, I could distribute the limit through each of these, saying that the limit of a sum is the sum of the limits. That's how this is going. So I'm following the rules that are handed to me, and those are the limit laws. Okay. So that numerator is going to be 14 minus 24, negative 10. The denominator is going to be 7, I think. Yep. Negative 10 sevenths. All right, let's try another one. Finally making it through. Oh my gosh, what is this? Okay. All right, we got a 2026. Lots of things going on. something I want to immediately explain is that the thing that's changing here, or the thing that's going anywhere, is the y. This is the limit as y approaches x. In other words, x is a constant in this case, and luckily it says right here x is not 0. So x is the thing that's not going to move. These y's are the thing that are going to move to x, and immediately you see a problem that if I plug x in for y, I'm going to have 0 over 0. So I definitely have more work to do. You might recognize a formula for the denominator here, and that will take us home immediately, but I'm going to kind of motivate that formula a little bit. So before I crush this, I want to make some observations. This 2026 is obnoxious. So what I'm going to do is figure out, I'm going to switch that with a smaller number and then hope that I can find some sort of pattern. All right, so bear with me. We're going to do a lot of multiplication. I'm going to start with 2. What if I had x squared minus y squared? Well, I know that one. That one is the same thing as x minus y and x plus y. Okay, that's famous. Same with this was pretty darn famous too. X cubed minus y cubed. That's going to be the same thing as x minus y times x squared plus xy plus y squared. Okay, so that's called the difference of cubes. If you don't believe me, simply grab this, distribute it through, and see that after you do all the distribution, this is what you get. Let's do maybe a few more. Let's see if we had x to the 4th minus y to the 4th. Well, that's the same thing as x squared squared minus y squared squared. And I see a difference of squares. Okay, so that is x squared minus y squared times x squared plus y squared. Oh, and I know how to factor this. This is the same thing as x minus y times x plus y times x squared plus y squared. Okay. Shoot, I'm kind of breaking a pattern. Notice this polynomial, or this factorization, was an x minus y times some big polynomial. And then this was an x minus y times some polynomial right here. Let's see what happens if I multiplied through these guys, and let's see if we can pick up on some sort of pattern. In particular, is there a way that we can guess what this extra part is going to look like? Let's see. Let's do x minus y. So let's just FOIL this. This is going to be x cubed for the first. And then we got x times y squared plus x times y squared. For the outside step, plus y times x squared. Nice. And then plus y cubed. Okay. I'm going to kind of reorganize this. This is the same thing as x minus y times x cubed plus x squared y plus x times y squared plus y cubed. Okay, so here's what I'm noticing. This exponent is always one more than this exponent right here, or put in the same way, this exponent on this side with this extra polynomial is one less than the original exponent. Let's see if that works here. Notice that I have a 2 right here and a 3 right here. I have a 1 right here and a 2 right here. Okay. Another thing to observe is the exponents of x seem to be decreasing, while the exponents of y seem to be increasing. All right. So, also, I guess another important thing is that we have a 4 right here, and there are 4 terms in this extra polynomial piece. We have a 3 right here, and there are 3 terms in this extra polynomial piece. This next time, I'm going to go backwards and make a guess for what x to the 5th minus y to the 5th is, based on this pattern that I've kind of observed, and see if it works. So this might take a little bit, but let's just see. X to the 4th, my guess is y to the 5th, or excuse me, x to the 5th minus y to the 5th is going to be the same thing as this. Grab that x minus y out front. and then x to the fourth. So I'm like redoing this pattern except for x to the fifth minus y to the fifth. So x to the fourth plus the exponent is going to decrease by 1, x to the third power, and then a y will show up. X will decrease again, x to the second power, and then a y will show up, but with one more exponent, plus x times y cubed, and last but not least, plus y to the fourth. Okay? Okay, this is going to be the same thing, distributing. It looks like I'll have an x times x to the fourth plus x cubed times y plus x squared times y squared plus x times y cubed plus y to the fourth. So I grabbed this whole thing and distributed into the x. But then I'll also have a minus y times that same thing. X to the fourth plus x cubed times y plus x squared times y squared plus x times y cubed plus y to the fourth. Oh, geez, so exhausting. But let's see what happens. I think distributing this x through all these guys on the top here, I think what I'll get is an x to the fifth plus x to the fourth times y plus x to the third times y squared plus x squared times y cubed plus x times y to the fourth. All right. Now distributing this negative y through this guy, I think what I get is a negative y times x to the fourth. That's also known as negative x to the fourth y. Negative y times x cubed times y, that's also known as negative x cubed times y squared. Negative y times x squared times y squared, that's going to be negative x squared times y cubed. And then I have a negative y times y to the fourth. Oh, excuse me, I skipped one. Negative y times x times y to the fourth. Negative xy, excuse me, negative y times x times y cubed is negative x y to the fourth. And then last but not least, I got this minus y to the fourth. And hopefully I've set this up in an appropriate way. Indeed, all these middle terms cancel. And, oh, and hopefully you guys are probably screaming at me for my blunder right here. That should be y to the fifth. Negative y times y to the fourth is negative y to the fifth. And all I have left, as we were hoping for, x to the fifth minus y to the fifth. Okay. Indeed, in general, x to the n minus y to the n is equal to x minus y times x to the n minus 1 plus x to the n minus 2 times y to the first, if you so choose, plus x to the n minus 3 times y squared. Notice that this exponent, or this exponent and this exponent, should always add up to n minus 1. N minus 3 plus 2 is n minus 1. And this pattern continues, plus dot, 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 until we're down to maybe the x's, and then we'd have y to the n minus 2. And last but not least, y to the n minus 1. So hopefully it's obvious why I'm mentioning this identity. It's not fun for me as a mathematician to just say that something is true and then not prove it. I've given you an idea for how the proof looks, but more importantly, I think to prove this officially, you have to use this thing called mathematical induction. I hope that everybody in this class is well versed with mathematical induction, but based on the past few times I've taught calculus, that is not the case. But I'd be really happy if you know how to prove this. It's not too bad with induction. You just got to know what you're doing. So why am I saying all this? All of this was motivated for hopefully a method on how to solve this limit right here. Indeed, we just found a way to factor the denominator. So let's use it. Taking it down here. what I have is the limit, it doesn't have to be that small, as x approaches y, nope, I think it's y approaches x. As y approaches x, right, of x minus y divided by, I'll write the limit again, just so we're good. X to the 2026 minus y to the 2026. But now we have a formula. This is equal to the limit as y approaches x of x minus y. It's going to be a mess in the denominator. Then we have x minus y, and then x to the 2025 plus x to the 2024 times y plus x to the 2023 times y squared, okay, plus plus at some point we're going to have an x, and then it would be y to the 2024, and last but not least, it'd be y to the 2025. Okay. But what's changing here? Well, first of all, we're very happy here. Those guys cancel. So all I have left is this 1 divided by this huge gross polynomial. But recall, y is the thing that's moving. This is not going to move at all. X is just some number that's not 0. Y, all of these y's are going to turn into x as we take the limit. In fact, I think there's no issue with taking the limit anymore. This denominator is always positive. This is equal to 1 divided by, this x to the 2025 stays the same. And then I will have an x to the 2024 times x, right? Because y was just limited to x, all right? And then plus x to the 2023 times, not y anymore, x squared plus ... This process continues. X times x to the 2024. That's plugging x in right here. And then lastly, I'll have an x to the 2025. Know your exponent rules. What I think I have, this is 1 divided by x to the 2025 plus exponent rules. You add these exponents. X to the, 2025 plus x to the 2025 plus ... plus x to the 2025 plus x to the 2025. But how many times have I added x to the 2025? As I was mentioning earlier, I think 2026 times. Giving me a final answer of 1 divided by 2026 times x to the 2025. All right. All right, that was a long one. Oh, gosh. So we got infinity going on now. All right, let's see what to do. My favorite thing to do is multiply by 1, so that's what I'm going to do. Again, I'm thinking difference of squares. If you ever see a square root, honestly, it's not a bad move to just immediately assume difference of squares is going to show up. And if it isn't helpful, then you'd soon learn that. Minus 2x. This is all divided by square root of, oh, and I should mention, why is there even a problem at the beginning here? Notice what happens if I plug infinity in. This part right here is infinity, but then I have minus infinity, okay? And recall that infinity minus infinity is indeterminate form. You have more work to do. Nope, you have more work to do. So I'll write that down. All right, back to where I was. Sorry, I instinctively saw the problem and forgot I was in a lecture video. X squared plus 3x plus the square root of x squared minus 2x. All right, so why was that helpful? Well, I think the numerator is a nice difference of squares. This is the limit as x approaches infinity of something squared minus something else squared. That's going to be the square root of x squared plus 3x. And right here we have the square root of x squared minus 2x. This is all divided by the square root of x squared plus 3x plus the square root of x squared minus 2x. All right, let's see. This is equal to the limit as x approaches infinity of x squared plus 3x, that escapes the radical, minus, also don't lose parentheses here, it's a common mistake, x squared minus 2x, all divided by this gross nonsense in the denominator, x squared plus 3x plus the square root of x squared minus 2x, all right? Okay, I'm seeing some simplification, not a ton though. I think I'll have a limit as x approaches infinity. Looks like we got this, distributing the negative. The x squareds will cancel in that numerator, but then I'll have a 5x. All right, so I still have an x character. The denominator does not change. Okay, we have more thinking to do. Okay, I think I'm seeing an idea. Watch this. I'm gonna make a step, and I just need you to confirm that it's actually true. So I'm force undistributing an x squared. Don't believe me? Just check my work. Grab the x squared, distribute it back. X squared times 1, oh, that's x squared. X squared times 3 over x, oh, that's 3x. Ah, nice. Same thing here. I have an x squared distributing to a 1, that's an x squared. X squared distributing to negative 2 over x, that's negative 2x. All right, so I haven't fumbled yet. What to do next? Well, I think this is the same thing as the limit as x approaches infinity of 5x, all divided by, I have the square root of x squared. In your brain, you should think, oh, that's the absolute value of x. But look at where x is headed. X is very, very, very positive. So I think that the absolute value of x, or excuse me, the square root of x squared is really just x. All right, and maybe you're seeing why we're very happy here. This is the same thing as the limit as x approaches infinity of 5x divided by x times the square root of 1 minus 3 over x plus the square root of 1 minus 2 over x. And x's cancel. No longer have infinity over infinity. Oh, by the way, I didn't mention this. I really should mention this. This was still a problem because it was then infinity over infinity. And that's why I couldn't pass the limit through. A lot of people would see that and go, oh, so it must just be 1. And the answer is no. In fact, I think this is an example of why that's not the case. I don't think we're about to get 1. Maybe we will. Okay, the limit of a quotient is the quotient of limits. The limit of a square root is the square root of limits. And the limit of a difference is the difference of limits. In other words, what I have is this is 5 divided by the square root of 1 minus 3 times the limit as x approaches infinity of 1 over x. All right? Plus the square root of 1 minus 2 times the limit as x approaches infinity of 1 over x. But as we mentioned in the last theory video, this is 0. Giving me 5 divided by the square root of 1 plus the square root of 1. Final answer, 5/2. Not 1, okay? So be careful with those infinite limits. All right, let's see how we're doing. How many more we got? 1, 2, 3. All right, I think we're doing all right. Ooh, this one looks interesting. All right, so I got the limit as r approaches 0 of 121r minus 1 divided by 1 minus 11 to the power of r. 121 to the power of r. Okay, let's see what happens if I plug 0 in. 121 to the power of 0 is 1. 1 minus 1 is 0. Not a problem yet. Plugging 0 into the denominator, 0 in right here, that's going to be 11 to the 0, that's 1. 1 minus 1, oh, we do have a problem. But, oh my gosh, this is like really more of a lesson on difference of squares. You got to love the difference of squares, because I am seeing that this is the same thing as 11 squared to the power of r minus 1 divided by 1 minus 11 to the power of r. But that's the same thing as the limit as r approaches 0 of 11 to the power of r squared minus 1 squared. Okay, 1 is the same thing as 1 squared. 1 minus 11 to the power of r. And you might be like, why are you writing it like that? And hopefully you understand that that is because this numerator is a nice difference of squares. We have the limit as r approaches infinity of 11 to the power of r minus 1 times 11 to the power of r plus 1, all divided by 1 minus 11 to the power of r. But actually, I'm going to stop and do that trick I did prior and say that's negative 11 to the power of r minus 1. Okay? Why? Because now I recognize that these guys cancel, giving me this is the negative limit as r approaches infinity of 11 to the power of r plus 1. And somewhere along the way, I switch 0 to infinity. Sorry. Should be r to the power, or r approaches 0. And this is the same thing as negative 11 to the power of 0 plus 1. And that is the same thing as negative 2. And I implicitly use something here that I can pass this limit through this exponential function. I'm cheating. We don't know we can do that. In a second, though, we will retroactively prove that 11 to the power of r has this quality of being differentiable, and all functions that are differentiable are also forced to be continuous. And we don't know what continuous is yet, but what I just used was the fact that 11 to the power of x is indeed continuous everywhere. Okay. So that one wasn't too bad. I like that one a lot. Okay. This one's crucial. Finally, we're able to use this limit that we proved in the theory video. We know that the limit as theta approaches 0 of sine of theta divided by theta is equal to 1. That's crucial. And that is going to tag along with us as we crush this limit. But even bigger than that, I think what I can also say is the limit as theta approaches, here, let me say this. The limit as, best way to do this. X approaches a of sine of g of x divided by g of x is equal to 1 as well, as long as the limit as x approaches a of g of x is equal to 0. All right. So if this thing inside of the sine is the same as the thing in the denominator and they both go to 0 as we take this limit, then we can be confident that that limit is going to be 1. So why am I saying that? Let's observe. We got to remember some trigonometry here. This is the same thing as the limit as theta approaches 0 of cosine of 4 theta divided by the sine of 4 theta times the sine of 3 theta. All right. Now, I'm noticing this. This sine of 3 theta is missing something. It needs a 3 theta in the denominator, okay? Because I want to be able to take a limit here, and I want that limit to behave nicely. Notice I have a 0 over 0 situation, so I can't just pass the limit through. So how am I going to force a 3 theta to show up in the denominator? Yeah, you guessed it. I'm going to multiply by 1. Okay, in a similar fashion, what I think I want in this denominator right here, this is the same thing as the limit as theta approaches 0. I'm going to multiply in the denominator also a 1. In the denominator, though, I want a 4 theta in the denominator. This is all happening in the denominator. Okay, let's check this out. Okay, so simplifying, I think that this is the same thing. Ooh, also this spare theta right here and this theta are going to cancel out. That's nice. And I think I have a 3 right here. That's simply a number. I can take that outside of the limit. And I have a 4 in the denominator. I can also take that outside the limit. And here's what I think I would have. I would have 3/4 times the limit as theta approaches 0 of, let's see, cosine of 4 theta divided by, in parentheses, sine of 4 theta divided by 4 theta times the sine of 3 theta divided by 3 theta. So why am I making any progress right here? Because I know that the limit of a quotient is the quotient of limits, and the limit of a product is also the product of limits. So this is the same thing as 3/4 times, in my numerator, I got a limit as theta approaches 0 of the cosine of 4 theta, all right, times the limit as theta approaches 0 of sine of 3 theta divided by 3 theta, all divided by the limit as theta approaches 0 of sine 4 theta divided by 4 theta. Okay. All of these limits are famous. We proved this one in the last theory video. The limit as theta approaches 0 of the cosine of theta is equal to 1. Right? So and well, let's see. I technically should do a little bit more motivating. I do see that this isn't just theta. That is 4 theta. So I guess I'm taking a little bit of liberty to kind of cheat a little bit. Do I want to spend time explaining why it's still 1? I don't think so. Maybe in the future. Or maybe in class. You guys can ask me, how is this one also 1? But this one's famously 1. And this one is 1. As long as this holds. Okay. Giving me a final answer of 3/4. All right. How many more we got? One more. All right, guys. Final sprint. Let's do this. Okay, we got an absolute value. We got the limit as w approaches 9 of w squared minus 81. Geez, yet again, another difference of squares. divided by the absolute value of w minus 9. Okay, so my first observation is that this denominator is going to depend on which side of 9 w is. So I'm going to break this into a case-by-case scenario. Let's first calculate the limit as w approaches 9 from the left of w squared minus 81 divided by the absolute value of w minus 9. If w is approaching 9 from the left, that implies that w is less than 9. And that implies that w minus 9 is less than 0. But that implies that by definition, the absolute value of w minus 9 is equal to the negative of w minus 9. Okay, so check your absolute value definition for why that is true. I have a sheet for it on Canvas. And that was helpful because that changes the limit. Then our limit is as w approaches 9 from the left of w squared minus 81 divided by negative w minus 9. Okay? This is the same thing, so that I'm going from here to here. That's the same thing as the negative of the limit as w approaches 9 of w minus 9 times w plus 9, all divided by w minus 9, and we're happy with these, giving me a final answer of negative 18. Okay, hopefully the other side of the limit is the same. So I'll say now find the limit as w approaches 9 from the right of this w squared minus 81 divided by w minus 9. W approaching 9 from the right implies that w is bigger than 9. Oop, that's a 9. I'll write it like this. Kind of reading from left to right. And that implies that w minus 9 is positive, and that implies that the absolute value of w minus 9 is just going to be w minus 9. And that changes our limit. The limit as w approaches 9 from the right of w squared minus 81 divided by, and I can change this denominator. I know it's simply w minus 9. But this is equal to the limit as w approaches 9 from the right of w minus 9 times w plus 9, all divided by w minus 9. W minus 9s cancel, and we are happy because this is positive 18. What did we get the last time? Oh, shoot, negative 18. So what I can say is that does not equal negative 18. Therefore, left-hand limit and right-hand limit don't match. And therefore, the limit as w approaches 9 of w squared minus 81 divided by the absolute value of w minus 9 does not exist.